SpaceX engineers integrated Starship's full-stack architecture with autonomous landing and high-thrust vectoring. Instead of trying to build a bigger gas tank, they changed how the rocket thinks and moves. They replaced slow human controllers with a computer brain that checks data 1,000 times every second. This brain uses optical cameras, radar, and laser sensors to see the ground in real time. This is how they actually did it. By using a technique called Supersonic retro propulsion, the ship fires its engines against the wind while still moving faster than the speed of sound. This creates a massive cushion of fire that slows the 15-story building down from 2,000 miles per hour to a gentle halt in less than a minute. This transformation was only possible because of the Raptor engine. These engines are the most advanced in the world. They use a process called full-flow staged combustion, which makes them incredibly efficient. One Raptor engine produces 500,000 pounds of thrust. To understand that power, imagine the strength of 100 heavy-duty semi-trucks all pulling at once. But power isn't enough. You need control. These engines can change their power smoothly, just like the gas pedal in your car. They can go from 20% power to 100% power in an instant. This allows the ship to hover in place while the computer looks for a flat spot to land. Older rocket engines are more like an on-off switch. They are either at full blast or they are off. You cannot land a giant tower with an on-off switch. You need the precision that SpaceX built. Another massive part of this breakthrough was solving the heat problem. When a ship returns from space, it hits the atmosphere at 17,500 miles per hour. This creates temperatures of 3,500 degrees Fahrenheit, which is hot enough to melt most metals. Instead of using a shield that burns away like a candle, SpaceX developed Pika-X. This is a tough, reusable heat shield that stays on the ship. It can take the heat over and over again, allowing the ship to fly, land, and fly again within days. They also added grid fins, which look like giant metal waffle irons on the side of the ship. These fins act like steering wheels, catching the air to keep the ship balanced as it falls through the sky. Without these fins, the rocket would tumble out of control like a stick in a windstorm. +1. The victory was validated by the numbers. While NASA's SLS cost $4.1 billion per launch, one Starship mission is projected to cost about $10 million once it is fully working. Let's put that in perspective. One SLS launch costs 410 times more than one Starship launch. That same $4.1 billion could pay for 410 Starship flights. SpaceX is already flying its smaller Falcon 9 rockets more than twice a week, every single week. They have proven that they can turn space travel into a routine service, like a delivery truck for the stars. Meanwhile, Boeing's Starliner project cost $4.2 billion and hasn't even sent a crew to the moon yet. The gap between the old way of doing things and the new way is getting wider every day. We also have to look at the competitive scoreboard. China has been very vocal about their plans to land humans on the moon by 2030. For years, the US was ahead by 4 years. But because of delays with old-fashioned contractors, that lead dropped to only 2 years. China has a very strong record of hitting their deadlines. Their space station was built exactly on time. Their moon robots landed exactly where they were supposed to. This created a sense of urgency. The US needed a win, and they needed it to be affordable. By choosing the Starship lander, NASA moved away from the slow, expensive models of the past and embraced a system that is already being built and tested in the real world. The mastery of this system extends to how the ship handles fuel in space. Because you cannot carry all the fuel you need for a moon trip in one go, SpaceX developed orbital refueling. This is like having a gas station in space. One Starship launches and stays in orbit. Then a tanker ship launches and docks with it to transfer fuel. This was another thing people said was impossible. Moving liquid methane and oxygen at hundreds of degrees below zero is incredibly dangerous. If a valve freezes or a pipe leaks, the whole thing could explode. SpaceX solved this by creating a flexible docking system that keeps the fuel stable. They have already demonstrated that they can manage these cryogenic fuels with 98% efficiency. This means we can now send massive loads of cargo to the moon. because the ship starts its journey with a full tank while already in space. The landing legs were the final piece of the puzzle. The moon's surface is not a flat parking lot. It is covered in craters, sharp rocks, and soft dust. If a 15-story tall ship lands on a slope and tips over, the mission is over and the crew is stranded. Engineers built the landing legs out of a special titanium alloy that can flex under pressure. They act like the shock absorbers on a mountain bike, soaking up the impact so the ship doesn't bounce or crack. The computer brain uses its radar to find a spot that is flat within 15 degrees. It then steers the ship to that exact spot with the precision of a surgeon. This is a level of technical mastery that simply didn't exist 10 years ago. The consequences of this breakthrough are enormous. By making rockets reusable, we have turned space from a place we visit into a place we can live. The Starship can carry 100 tons of gear. That is enough to send a whole laboratory, a power station, and a year's worth of food in one single trip. Under the old system, you would need 20 separate launches to do the same thing. This reduces the cost of building a moon base by 90%. It also means we can move much faster. Instead of waiting years for a new rocket to be built, we can just refuel the one we already have and send it back up. Competitors like Blue Origin are also entering the race with their Blue Moon lander. This ship is about 15 stories tall as well, and it is designed to carry 3 tons of cargo with extreme precision. While it hasn't reached the flight frequency of SpaceX, it proves that the industry is moving toward this new model of high-tech autonomous landing. Blue Origin's BE-7 engine is another marvel, designed specifically to work in the vacuum of space for long periods. Having 2 different companies building these machines creates a competitive scoreboard that drives down costs and increases safety. It ensures that if one system has a problem, the other can keep the mission going. The future implication of this mastery is that Mars is no longer a dream for the next century. It is an engineering problem for right now. The same ship that lands on the moon can land on Mars. The same refueling system that works in Earth orbit can work in Mars orbit. We have built the infrastructure for a multi-planetary civilization. The impossible barriers of the past, cost, weight, and reusability, have all been torn down. We are no longer throwing away our best technology. We are using it to build a permanent bridge to the rest of the solar system. The timeline tracking shows how fast this is moving. SpaceX has gone from small grasshopper tests to full orbital launches in record time. They have already landed their boosters over 200 times. Every landing provides a mountain of data that makes the next one safer. They are iterating at a speed that traditional government programs cannot match. This is the power of strategic intelligence and rapid testing. By failing fast in the early days, they learned how to succeed every time when it finally mattered. The transition from science fiction to engineering reality is complete. The Raptor engine design specifically solves the choke point of older rockets. In a normal rocket, some of the fuel is burned just to power the pumps that push the rest of the fuel into the engine. That pre-burned fuel is then wasted and blown out the side. In the Raptor's full flow system, every single drop of fuel is eventually used for thrust. This creates a much higher pressure inside the engine, about 300 times the pressure of Earth's atmosphere. Imagine the weight of a skyscraper pressing down on a single square inch. That is the kind of force these engines handle. This high pressure is what allows a smaller engine to lift a much heavier ship. It is the core of the technical victory that made the Starship lander possible. When we talk about the competitive race, we have to look at the numbers of the other players. ULA, a partnership between Boeing and Lockheed, has a rocket called the Vulcan. It is a great rocket, but it is not fully reusable. Each launch costs about $100 million. While that is better than the SLS, it still cannot compete with a ship that you can refuel and fly again for the cost of the gas. The market share is already shifting. In 2023, SpaceX launched more mass into orbit than the rest of the world combined. This isn't just a lead, it is total dominance. It shows that when you solve the engineering problem of reusability, the economics follow immediately. The autonomous landing system also solves a major safety issue. On the Apollo missions, Neil Armstrong had to take manual control of the lander because the computer was heading toward a field of boulders. He had only seconds of fuel left when he finally touched down. With the new autonomous system, the ship doesn't get nervous. It uses millions of data points to find the safest spot in a fraction of a second. If the primary landing site is blocked, it can instantly calculate a path to a secondary site. This reduces the risk to the astronauts and ensures that the 100 tons of expensive gear actually makes it to the surface in one piece. We are also seeing a change in how these ships are built. Traditional rockets are made of expensive carbon fiber or specialized aluminum. They are built in clean rooms by people in white suits. SpaceX builds Starship out of stainless steel in an open-air shipyard. Steel is much cheaper and easier to work with. More importantly, steel handles extreme heat better than other materials. This was a strategic decision that everyone laughed at first. They called it a water tower rocket. But steel is what allows the ship to be repaired with simple welding tools and flown again quickly. It is a working man's rocket, designed for high-frequency use rather than being a delicate museum piece. +1. This shift in materials and design is part of a pattern recognition strategy. SpaceX looked at the history of aviation. Early planes were made of wood and fabric and were very fragile. Modern planes are made of metal and can fly multiple times a day for 30 years. To make space travel routine, you have to build rockets like airplanes, not like missiles. This is the strategic intelligence that led to the stainless steel design. It prioritized durability and ease of repair over slightly lower weight. That decision is now paying off as they prepare for the high-intensity schedule of the Artemis missions. The consequences of failing this mission would be a loss of resource protection. The lunar South Pole is believed to contain vast amounts of water ice in craters that never see the sun. This ice is the oil of the solar system. You can melt it for drinking water, or you can split it into hydrogen and oxygen to make rocket fuel. Whoever gets there first and establishes a routine landing system will control the most important resource in space. By mastering the Starship lander, the U.S. is securing its place in the future economy of the solar system. It is a justice consequence for the years of investment and risk-taking. +1. Pattern recognition also tells us that the first company to master orbital refueling wins the long game. Once you have gas stations in orbit, the entire solar system opens up. You can send missions to the moons of Jupiter or the rings of Saturn without needing to build a mega rocket for every single trip. You just use a standard Starship, fill it up in orbit, and go. This is the transformation from a scarcity model of space travel to an abundance model. We are moving from a world where we can barely afford one mission every 10 years to a world where we can send missions every month. The human decision-making at the heart of this was the move toward rapid prototyping. Instead of spending 10 years designing a perfect rocket on paper, engineers built a version, flew it, watched it blow up, and then fixed the problem in the next version. This fail-fast mentality is common in Silicon Valley but was considered dangerous in aerospace. However, it proved to be much faster and cheaper in the long run. It allowed for competence demonstration in real-world conditions. Every explosion in the early days was just a lesson that made the final version of the Starship lander more reliable. The competence hierarchy in the space industry has been completely reshaped. It used to be that only government agencies had the technical mastery to reach the moon. Now private companies are leading the way. This competition has forced everyone to get better. NASA is now more like a customer, buying rides to the moon rather than building the whole system themselves. This allows them to focus on science and discovery, while the private sector handles the trucking part of the job. It is a more efficient division of labor that benefits everyone. We must also talk about the system mechanics of the grid fins. These are not just flat wings, they are a complex mesh that allows air to flow through them at high speeds, providing much more control than a solid wing would. This is why the ship can stay upright even during the belly flop maneuver. This maneuver is where the ship falls flat through the atmosphere to slow down and then flips vertical at the last second to land. It looks like a magic trick, but it is pure physics and high-speed mechanical control. It is the final victory of engineering over the constraints of the old way of flying. The impact on the global competitive scoreboard cannot be overstated. When other countries see a private company landing 15-story rockets like it's a normal Tuesday, it changes their strategic intelligence. It forces them to rethink their own programs. It has sparked a new space race that is faster and more exciting than the first one. This time, the goal isn't just to leave a footprint, it's to build a highway. The technical mastery demonstrated by the Starship lander is the first paving stone of that highway. The future of humanity is now tied to these machines. Every successful landing is a step toward making us a multi-planetary species. The information hunt is over. We have found the solution to the problem of high-cost space travel. The pattern recognition shows that the costs will continue to fall as the technology matures. We are at the same point in space travel as we were with the internet in the 1990s. It is about to explode into every part of our lives. The impossible has become routine. SpaceX didn't just land a rocket, they made it routine. Over 200 landings while Boeing's Starliner hasn't flown crew, and Blue Origin hasn't reached orbit. The impossible became infrastructure. Now Starship aims to do the same at 10 times the scale, turning Mars from science fiction into engineering problem.